Thanks for having me here. It's a pleasure. I'm representing EOS and the EOS Innovation Department. So what I'm going to talk about is the next generation of technologies that we are developing at EOS to bringing into our future machines. And the Hitoshi asked me to present you basically 3 topics out of interest. So the first topic is around very small components. So how small can we get? How detail resolution optimized can we optimize for certain components within different levels. The other topic that he asked me to present was about how fast can we actually go? What is our future strategy to make additive more appealing for future business cases? And the last but not least, and also very important one that will have a dramatic effect on all the other innovation streams that we're following is building in a more intelligent manner. And I have some examples here about how we are actually accomplishing that. So we'll start with how small can we get? And how small can we get is basically about 2 streams. So the one is a technology which we call pulse laser modulation, where you basically go away from the continuous wave exposure and you only expose in a different regime where it's actually having a benefit. So it's combining 2 worlds. It's pulse laser modulation and the continuous wave operation. And then a hardware modification that we can also offer about how small can you actually get by doing hardware modifications. And there we'll show you a few components and examples. So typically, you try to make your life as easy as possible. So going directly into a hardware modification, if you start coming to a boundary condition or an end of what is possible from the detail resolution, and you directly go to hardware, it would be like not so wise because it's more difficult, so to say. And therefore you try to make your life itself easier. And the first adaptation to that would be using different recoating methods. Recoating methods such as a rubber blade or a brush recoater or silicon or whatever, like soft recoating technologies that are out there that help you to make fine structures buildable without sacrificing and compromising quality. So this is, so to say, the first step. A next modification where I myself have spent a lot of time is in the process parameter optimization. So not all process parameters are best suited for all the different geometries that you build. And it is very often required that the application engineer or the engineer that is designing a component has the possibility to have an open parameter set to modify and fine-tune parameters for a specific application. So typically the EOS parameters, they have you a robust and good and solid quality, but partners such as Exam from EOS, they have very good experience in how to optimize exposure parameters for a specific customer problem. The parameters that you can modify in EOS machines, they're completely open. So whether it's the layer thickness, the scan speed, the power, the hatching style, the pattern, whether you have a contour exposure only or hatching exposure, you can break it down to very deep levels. But experts such as in Hitoshi's team or Exam's team, they can help you optimize the exposure for a specific problem. Pulse laser modulation, as mentioned, has very good possibilities where needed. So if you have a geometry that has bulk and thick features, but also intricate fine features, you can combine those 2 worlds. It's not a problem at all within EOS Print software to have those 2 or even those 3 systems or technologies combined. So all of that is possible. And last but not least, and I will come to that point, this is the most challenging, the most demanding application is if you go into hardware modifications. So whether it is through some basic optical changes or really a radical machine modification. But you as a customer, you will never be left alone. So whether it's EOS through an innovation project or with our colleagues from AMCM, which is a sister company to EOS, we can help you to generate technology, whether it's through software modifications or process parameter optimizations, or through a machine adaptation to tackle your specific problem in order to help you. So we help you in a very holistic manner, in a holistic way. So on pulse laser modulation, I want to elaborate a little bit deeper because most customers don't know that with pretty much every machine, starting from M290, M404, M300, also metal-based technologies, and EOS Print 2.8 as a version, all the systems, they are pulse laser modulation operatable. So it's only a software feature that you can activate, but it's hardly used. So a lot of customers don't have experience of how to using them best, and there's where we offer you also help. And what you can achieve is really, really cool and amazing. So here's a few examples. For instance, in Inconel. Inconel is a material that is very heat resistant. It is at the same time also corrosion resistant. So typically a lot of customers, they wouldn't approach us with Inconel as a material for heat exchangers. But if you're able to get the wall thickness thin enough, the thermal conductivity doesn't really matter that much anymore. The performance of the part can be substantially increased by getting the walls thin enough for a specific application. And here you can see a single line exposure, and those single line exposures you can get down to about 120 micrometers thin walls that are actually watertight, up to 2 atmospheres pressure, which we've tested. So if the application allows, and you don't need a watertight structure, but a heat exchanging structure or surface area, so to say, you can go even thinner than that. So 90 microns, in some very specific cases, you can even go a little bit lower than that. So I think that's already pretty good. And here's an example that you can all see also on the XAM booth as a gyroid structure with beams of around 120 microns thin strut. So those parts out of Inconel, they feel unreal, because if you have them in your hand, they feel more like aluminum because they're so light, but it's an Inconel structure. So it's really, really interesting. So you're welcome to come by our booth and experience that for yourself. But same in aluminum. So a lot of customers ask us, like, how thin can you print an aluminum? The exact same application, or as a CPU cooler. This is an application internal project that we have from our application engineers. And in aluminum, it depends a little bit also on the thermal properties of the powder as well as the material itself. You cannot go that much down to have watertight structures. So in aluminum, it's more in the range of 150 microns to have it water and airtight, but it's actually workable. And how do we test it? It's just an internal geometry, how we validate our process tests. We do a submersion test. So basically we print a specific probe that has a area that contains those very fragile components, that is also shielding them, because 200 or 150 micron thin aluminum is very fragile. It behaves more like a aluminum foil. You can very easily break it. So therefore, it is encapsulated here in these structures. You just connect it to a pressurized hose, and then you submerge it into water. And if you see bubbles coming out, you know that you have to go back into the process parameter optimization. So we did that test for Inconel and for aluminum. So 120 to 150 microns is what you can typically reach. So this is all accomplishable doing just pulse laser modulation, so basically a software feature. Another component that I have also on the booth with me is an Eiffel Tower. And if you see that Eiffel Tower here, it's really small, really, really small. And if you want to print that, typically what you see is that you have areas where the detail resolution is really not met, or you have these handlebars that can get really, really delicate and small, or these arc structure can have a lot of particles being still stuck to that, or that the base plate doesn't look very, very neat. And with pulse laser modulation, where you apply these parameters only on the region where it's necessary and has a benefit, you can get this significantly improved. And I have here a picture where you can see it directly left and right. So here on this component, that little Eiffel Tower, really, really small parts. without pulse laser modulation or with pulse laser modulation activated. And you can see it up here, how this structure really looks different. Everything here is like smeared together. There's no real sharpness or crispness of these individual beams there. Here you can see them better. Or in region where this handlebar is, here you have powder or bars that are in the like horizontal orientation. They wouldn't be printable at all. And here you can print this handle perfectly fine. And this is all printed with hard recoating blade. Or these arc structures, so they tend to have, like in Inconel, depending on the diameter, these like bad downskin surfaces. This can all be corrected. Or even like in overhang regions, this kind of curling effect can all be healed quite substantially by just a software feature and a parameter optimization. And here's another like extreme example, in a very extreme case, where we have used a machine where we have like altered the focus diameter very substantially. So typically the focus of an EOS standard machine is in the range of 80 microns. And if you want to go smaller and smaller and smaller because your application requires it, your tool diameter, so to say, is your limiting factor. And sometimes it is required to get the tool diameter smaller. So here we have a modified system with stainless steel powder where we've generated this chain link structure. And the real fascinating part is, I mean, look at that, it's really, really small. Those features, those individual brick links, they have a diameter of about 80 microns. Here we're using a substantially different powder. So the powder is finer, it's very difficult to recoat. So it's a modified recoating technology that we use, and substantially smaller focus. So also come to the exam booth and see the part for yourself. It is really cool. You can play it. It's a tough part. It's not so easy to break, but don't try to force it. We have some other samples that you can try to break and you will not be successful. So pulse laser modulation and FDR technology. And as mentioned, through EOS and our cooperation with Exam or our sister company AMCM, we can offer you a holistic approach. On the other hand, was asked is, what are we doing in order to win the laser race? And it all comes down to like that. Your part per price is everything that matters. If your business case is not right, most likely you will not go into additive manufacturing. If you can conventionally manufacture your component, but the additive path is too expensive, you typically won't do it. So what we need to do is we need to get the cost per part down dramatically. Will we be able to, as a general, be able to lower the machine price that dramatically that your business cases make sense? Most likely not. So what you have to do is you have to have a relatively stable machine price, but you have to double, triple, quadruple the throughput of that system in order to get more parts for the same money, so to say, out of the same machine. At the same time, your quality, your components, your material properties must be right. They must be in your quality range, what you expect them to be. You have to have the right materials available, not only the standard materials that EOS or the powder manufacturers offer, that materials that are best for your specific application. And in general, the technology must get greener. And with our beam shaping technologies that we're currently developing and that we're working with, we're addressing all these topics at the same time. And I have some really, really cool examples of how it's actually being accomplished. And it, as mentioned, initially, again, it comes all down to price per part. This is the price acceptance level, whether it's euro per cubic centimeter or yen per cubic centimeter. That's all that matters. If your business case is not right, you will not go into additive manufacturing, and we've all lost. Therefore, we try to really address this by having more advanced, more intelligent systems. And more intelligent system does not mean you put more and more lasers onto a machine. It is you put enough amount of lasers onto the system that do the job in a more smarter manner. So one technology that we are developing is called internally Big Spot, based on a new scanner. So that scanner is a like prototype scanner that can deliver up to 3 kilowatts down into the powder bed. And it's in theory nothing else than a 3-axis scanner. So it has a third axis that can, like on the fly, decouple and defocus the beam up to 1 millimeter in diameter. The charming part about that scanner is it is capable to deliver up to 3 kilowatts, and it has some very intelligent sensor technologies inside that take care about topics such as thermal shift. The reason why I have here behind 316L or Inconel or aluminum that check mark is we have tested that scanner quite thoroughly with those materials under standard process conditions, so to say. So we have a Formula 1 race with a half pressed down pedal. So instead of using 1 or 2 kilowatt of power, we've just tried to replicate those processes. And the scanner performs in the exact same manner. But I mean, I'm trying to play here a little bit with stereotypes, and Germans have stereotypes about Japanese people that you really like racing. And I came to the exam booth, and there you have this drift race car coming over, and I think it's just cool. So if you drive a race car on a standard motorway, there's no fun inside. So what happens if you really unleash the power? And that's what you can basically see in this process. So here's a direct process comparison with the exact same quality results, where the right side is being processed at 1 kilowatt with a significant, substantial, faster scan speed. And here on the left side, it's a standard process that you know. So here, that is the real fun. So because I think it's so cool, I will just replicate it again. So just that you know, this is same quality. The parts, if you see them, if you have them in your hand, they look absolutely identical. And it's not done by having 2 or 3 or 4 lasers on one system. It is a single laser machine. But to be very, very frank, again, I'm trying to use metaphors or similar stories. Using a standard tool to solve all the world's problem is not the best idea. And again here, if you have a car and your car breaks down and you bring it to a shop, the person that works on your car has a set of different tools that he can use in order to fix the problem on your car. In the additive manufacturing arena and world, the tool of choice is always a hammer. Whether it's a 400 watt hammer, a 1 kilowatt hammer, a 2 kilowatt hammer, a hammer stays a hammer. If you put a rubber blade around it, it doesn't matter. It's not the right tool that does the trick. So basically, we have developed EOS technology to a certain extent that you can switch the tool, so to say, which is a Gauss standard beam, within milliseconds to any arbitrary beam shape that you can imagine. So it's very sophisticated technology that we use for research purposes. And I had the discussion internally whether I should show this picture or not, because it's a pre-development technology. It is not technology that you can buy. It is not technology that you can just easily operate with. But it has some really, really interesting features. It is operatable at a significant higher powers than 1 kilowatt. And it has a high speed, a high image resolution camera there that can take up to 50,000 pictures per second of the process, monitoring window, where we do research, where we do a fundamental understanding of what is the right tool for a specific material to absorb more energy in a shorter period of time. And that's a quick snapshot of different beam shapes that we're experimenting with. So whether it's a donut-shaped style that is very commonly known through NFX lasers or from Nlight, or a multimode laser that delivers something like a top hat profile or a Gauss profile with different intensity levels, or even asymmetric beam shapes are possible. So, and switching between those beam shapes can be accomplished within very, very short periods of time, so milliseconds. And here's some process results. I will not elaborate too much into detail which one is which, because there's a lot of IP, but you can very clearly see that they behave different. You see the spatter formation here of these videos. You see how much dust or clouds or condensate is being emerged from the melt pool. In some of those here, it is very interesting to see that those particles that are being ejected sometimes really fall back into the pool itself. So by having this technology available, we understand very well what advantages the different beam shapes have to the laser processing process itself. And here, like another example of how that translates into real world application. And I said initially, we don't want to have a competition of who is winning the laser race, who has the most lasers on the system, because that is only adding complexity. We want to do it smarter. And here we are operating that system with exact same laser power, but with different beam shapes for the different areas of the component. So here on the left-hand side, everything is being exposed with standard Gauss beam. Here on the right-hand side, the infill is being done with the top hat. The contouring is being done with a contour beam. And then we can also do beam splitting. So we have, like, instead of one beam, we have 3 of them that just scan everything at the same time. So exact same power setting, but you have a factor of about 2.5 faster on the right-hand side. One cooperation is already in existence with a company in Japan that is a pioneer in the 3D printing business. Especially in Japan, and very competent in doing so, is XAM as a company of NTT Data. So here we are talking about systems that are not standardly commercially available, but we are cooperating with our customers very closely to have their immediate feedback about how and which technology does actually make sense and how can we faster develop those. So cooperation partners are company like XAM or Technical University of Kaiserslautern or end customer KSB or Fraunhofer ILT. So all of those, they have a big spot M290 machine that can do that trick already today. So please approach us directly or those customers if you have research projects that you want to engage with those clients together. And here one example of what it can actually do to real case applications. So this is a part that was highlighted 2 years ago on the Formnext. And it's a tool changer made out of aluminum. And on an M3 with 4 times 1 kilowatt, we were capable to print over 35 kilograms of aluminum in less than 30 hours. So it's the deposition rate is really, really high. So that goes fast and speaks for itself. And the part properties are good enough for that specific application. Another derivative that you can get for beam shaping technology, because initially said this is very sophisticated, difficult to handle technology, but a standard product already out there can be acquired by our sister company AMCM. So it's 100% sister to EOS that has used as a base machine an M290, has added a different laser, so it's the NFX laser from Enlight, has done some modifications as well on the system in order to make it capable, and it can actually handle up to 2 of these NFX lasers inside one M290 system. And then you have those productivity gains directly onto existing technology. So, and this is smarter melting than most of our others are doing that today. Another example here is, a case that we have simulated only with KSB. So printed it was on a standard machine, but using that on an AMCM NFX machine, you would be able to print this Inconel impeller with 400 millimeters in diameter instead of in 135 hours in about 32 hours. So you don't want to wait days and days and days, and then something goes wrong, you have a power outage, or something goes odd with the machine in order to have a successful print. You want those throughputs significantly higher. And here we have technology that can deliver that already today. So if you have questions, we have also experts on the exam booth that can help you with those specific questions. And about Smart Fusion, I believe, is one of the biggest game changers in the additive manufacturing arena, because it makes really impossible prints possible. And it's all about smarter fusion, avoiding support structures. And some people do that through process optimization, process simulation upfront. They put a lot of application engineers, resources into optimizing for a specific problem. Here we have a tool developed that does that all automatically. So it's basically using the OT camera of the machine and is reading the thermal image and signature of that specific layer that was printed, and if it detects a certain overheating in a region, it can in the next layer correct and correlate for itself. So it's basically it's a machine that controls itself and adapts and adjusts the process where it's necessary. And the results are amazing. You have dramatic reductions in the print time, you have dramatic reductions in the area, material being used for these support structures, and you can dramatically save also post-processing time. So imagine having to break off all these individual supports here. That can be quite laborsome and is very often expensive manual work. So the best support structure is no support structure. But sometimes your geometry does not allow you to have no support structure. So EOS has developed technology that makes this obsolete. I have more examples here, like a tank from a partner called Launcher Space. So it's a propellant tank for Delta delivery device of satellite vehicles. So this stuff is really flying. So it's a structural component of that orbiter, but at the same time a tank device. And if you would have asked me, I'm now 14 years with EOS, 2 years ago, is that tank without support structure printable? And I would have said no way, this is like really impossible. And anybody that understands metal 3D printing knows that this is really a hard nut to crack. In this case, 300 millimeters in diameter, 400 millimeters tall, printed on the first try. No defects, no problems. The downskin is unmatched. The quality of the entire component is really out of this world. Another case is maybe something also for Hitoshi, or he likes, as I understand, dirt bikes a lot, a footrest of such a dirt bike. And here the business case is really challenging because this is a component that is highly stressed. Those devices, they have to take up a lot of load. They're manufactured out of titanium, and the only way to make that possible is to have at least amount of supports possible and building them in the best efficient way inside a process chamber. So you stack them on top of each other, and there's a LinkedIn video right now. If you go onto my LinkedIn site, you can see that, where the supports are that fragile that you can break them apart by hand. So the post-processing effort of this is basically zero. Another component that we've used is initially showed this big impeller. So this big impeller is from KSB, so real part. It's a seawater pump in really harsh environments being used with like post-processing, making it very difficult. So in a closed impeller where you have supports on the inside, to access those is always very tricky. Here, making this possible in Inconel printed on an M404 in a really short period of time. So it's a standard system with hardly any supports is really cool. And now, like a lot of people say, if you let the machine decide where to adjust the process, where you have significant overheating or not, the first question always being asked by customers is, how is the quality being affected? So here we had some initial tries because we had to optimize also the process here. That was one of the most challenging parts that we've ever printed. And this is one part that 75% built through. And instead of wasting and throwing 35 or 30 kilograms of Inconel away, we started to section this. We started to dissect the part exactly in the regions where we had the process adaptations and process adjustments happening, and did porosity analysis. And exactly those questions were being like answered by our laboratories. Do we have any anomalies? Do we see anything like happening? And even in the regions where the machine has had really difficult times also to print those, there is no process anomalies. So these pictures, they all show like perfect microstructure and perfect density. And here I highly encourage, so these are standard pores in a range that we expect them. You don't have like what I want to show, like nothing to hide directly even underneath the surface. And what I want to encourage you is, like, we need you as customers and feedback, that you come to us and show us your applications, your problems, that we together can solve them. And there I invite Hitoshi again, that he also tells you exactly how such cooperations can
Yeah,
work.
okay.
Thank you for your time.
ありがとうございました。ですね、今日紹介させていただいた、そのパルス、微細構造とサポートフリート、生産性向上。まだまだ市場に出てない技術もあるんですけど、AMCM っていう、カスタムの、機械を作る会社もあってですね、実はこのうちのおよそ8割ぐらいはもう今すぐ機械が欲しいということであればですね、ご提供できますし、実際にこういった技術を使って一回技術を検証してみたいということも、全然お答えできますので、実際にこの技術で作った部品とかはですね、ブースに置いてますので、ブースに来ていただければですね、日本語でいろいろと詳細の技術の打ち合わせさせていただけると思いますので、ぜひお時間許せばですね、お立ち寄りいただければと思います。本日はありがとうございました。